I'll do that, record on this computer. Okay.
Thank you.
Yeah, sure. So this is our 26th lecture for the FIS 140 course. And what we were seeing before was this, we're in the realm of nuclear physics. Let me see if I can get this perfect. So we were seeing that the key aspect of nuclear stability has to do with the fact that this system has a bunch of nucleons being held together. They have a binding energy, and essentially the expression for the binding energy is what I have here on the first line, which actually indicates that if all the constituents of a nuclei are actually completely separated, the energy that system has is higher than if they are all forming the actual nuclei, as it's been shown in these equations. This is simply the difference this is Einstein relating mass and energy, which is all the same subject. Okay, so this is the expression for the binding energy of a particular nuclei, and then we actually showed you last lecture, or I did show you last lecture, that the shape of the curve that actually describes the binding energy per nucleon as a function of the number of nucleons in a particular nuclei is sort of like this. So on average, you would say, probably 8.5 mega electron volt per nucleon is a good number to actually have in mind. But there are a few features that are very relevant that I was trying to make the point when the last class ended, is the fact that heavy nuclei here have lower binding energy per nucleon than lighter nuclei. And the maximum here is in nickel 62. Okay, so this is the most stable nuclei of all the elements in the periodic table because they have the highest binding energy per nucleon. So this indicates that at the end of times, the universe will be exactly this, a big nickel crystal. Okay, so these guys down here somehow have the same advantage, that if they are somehow put together, there's an energy excess associated to the processes that go on this side. Okay, this is rather cryptic at this point, but it's going to be made more clear when we go down the lecture. This graph here shows, this is the stability island, okay, in nuclei. So here we have the number of neutrons neutron number, the number of neutrons in the system in a particular nuclei, and this is the y-axis, and the x-axis is the number of protons. Okay, so if we go down here, we actually find out that the number of proton and the number of neutrons is almost the same, up to something like 20 something. Okay, up to when the A number, A is equal to N plus C, is around 40. Okay, so this is an interesting graph in the sense that it displays, for example, isotopes very easily. What are isotopes? Isotopes are elements, are vertical lines in here. For example, this guy over here has a lot of isotopes here. See, I want to try to make it bigger here. See, all these elements here have, I'm sorry, it's not very clear, but it makes the point anyway, that this is a vertical line, and all the elements, all the nuclei here have different values of N, but the same value of Z. So they somehow represent the same element with different number of neutrons on it, but the protons is actually what gives the ID to each one of the nuclei. That's one of type of processes, a constant n, okay? A constant, I'm sorry, a constant z value for a nuclei. A constant n doesn't with varying c's doesn't give much of a clue, but this other line it's relatively important. These are constant a values, since these blue lines here are constant value of a, and all the parallel lines that you can draw here to these blue lines are going to be constant a values for the nuclei. Okay, so this is interesting also because you can see how a nuclei that could be, let's say I produce somehow a nuclei which is very far up here, and you can say that the energy of this nuclei will benefit from actually going down this line and arrive to the region where you find that the nucleus are stable. So essentially, if you would plot the energy, the minimum energy configuration in a third axis here, you can imagine an axis coming out of here, and you can feel that this is some sort of a valley at the end, and you have some sort of parabolic bottom of the valley goes exactly where this line is. So roughly, it looks like a river at the end of the valley, essentially, at the bottom of the valley, and that's what essentially is in a way. And you can feel that whenever you move a nuclei away from this stable position, you will have a nuclei with higher energy. In nature, there are many nuclei, and in science, scientifically, we have actually been able to discover about between something like 2,000 and 3,000 nuclei. I don't have the number exactly, but what you have in the number of dots that you have in this table is about 300. Okay, so there are a lot of nuclei that are not stable, and there are nuclei that are stable. This 300 that you have here. Okay, so the question is, what happened with the unstable one? Well, the unstable one had to somehow, the word is decay or evolve to a position of stability. You can see that there are no nuclei, with above 220, about A to 20, there's no nuclear, there's no stable. I would say 210 essentially. About 210, they're above to, if A is above 210, there are no stable nuclei. So if you can, for any reason, make a nuclei up here, this guy will decay down here in a way. Okay, so to get to the stability value. So this is sort of a very important evidence that we have to take into account when we describe nuclear matter. Okay, so the question is, how do nuclei evolve when they are a bit away from this stability region? Okay, well, they have to decay. That's the word. How do they decay? They have to transform somehow. If look at a decay along this line, it will mean that the number of nucleons will remain constant, but what you're doing is changing the charge of the nucleons. So essentially, if you are up here, it means you have a lot of neutrons, and you transform those neutrons in protons, and when you do that, you start moving along this line over here. This is essentially what happened with nuclear decay. Okay, and we're going to be seeing some of those processes too. Okay, so to describe them briefly, let me change this slide. Okay. Oh, I forgot to mention. Yes, this is an important decay mode. You know, they are in the initial times of nuclear physics, you know, people discovered that some of the nuclei that they were around, they decay, and they found 3 modes of decay. And what did they do? They used the first 3 Greek letters to describe them: alpha, theta, gamma. Perfect. Okay, just as the COVID variants or something like that. So the first one was the alpha decay. The alpha decay is a charged particle that have a very small range of travel in space, because since it has charge, it collides with everything. Okay, the alpha particle, it's almost like it's not almost, it's a helium ion, completely deprived of the outside electrons. So if you remember last lectures, well, we have it here actually. This point over here is a very strong indication that a configuration of nucleons that have 4 nucleons and divided in 2 protons and 2 neutrons is a very stable one, because it has a very high value for the binding energy. So when you have protons and neutrons living inside the potential well, you can imagine this is a nuclear potential well inside a piece of material, nuclear material, and let's say this is, for the sake of purpose, this is an unstable nuclei, but you will have a lot of nuclear matter confined in this region between 0 and R. And what happens is, I'm sorry, and the particles inside the nucleus, inside this big nucleus, can assemble together in pairs. They do that, and also as 4 particles, with 2 pairs with 1 pair of neutrons and 1 pair of protons, and that particle can live in a confined space or a confined level inside the nucleus. So this graph over here represents the energy of the nucleus as a function of the radius. Okay, below R, you have a very strong nuclear force, and it doesn't really matter the electromagnetic interaction, because the nuclear force is so strong that and if it is attractive, it creates this very deep potential well with many mega electron volts depth here. So this supposed to represent something like radon. Okay, but radon has in particular this thing here that they can, the alpha particle that can form itself inside the radium can at one point traverse against this potential barrier here by tunneling and appear outside. But this is a fairly slow process. It is not something that you will have them there in a can one day and then all will be gone afterwards. No. This is a very steep barrier. This part of the barrier here is the electromagnetic interaction, which is very strong when you are away from the region where the nuclear force is strong. Here the nuclear force is overwhelmingly strong, and here is not. So what are we measuring in this graph here is the potential interaction between the parent nuclei here and the alpha particle that goes away, okay, afterwards. So if the alpha particle is around this region here, you feel the electromagnetic interaction. If it is within here, you only see the nuclear interaction, which is relevant for this purpose, okay? But these particles here have, this is a potential well. A potential well have energy levels, and the energy levels for a particle like an alpha particle inside the radon nuclei is a very well-defined number, okay? So this alpha particle that forms inside is actually bouncing back and forth between the walls of the inside the core of the nucleus, and after a while it has the chance to actually penetrate it and get out. And this is a sort of process that you can see, and if that happens, the alpha particle can carry away this much energy, 4.871 mega electron volts, which is a huge amount of energy compared to anything that has to do with electronic processes. And when it does that, it carries that energy away and produce a second nuclei. It moves from radon to radon. Radon, I'm sorry. This is a radium nuclei, and this is a radon nuclei. The pronunciation of the A here is the key. And so this has less number of nuclei. It has the difference is 4. See, this guy is 226 and this guy is 222. Why? Because the alpha particle went away. Okay, so when this alpha particle leaves this nuclei, the daughter nuclei that stays here is the radon nuclei. Okay, radon is a gas. Okay, and it's and it's still actually it's still very, very reactive in the sense that it decays continuously. So in some parts of the US, this is a real serious problem because this is a gas that you don't smell the gas, and it's radioactive particle lying around that can give you a lot of energy. How much energy? This here is oops, I'm sorry. This here is 0.2 mega electron volt gamma ray, which has a lot of ionization effects on humans or anything alive. So this living in this environment with the radon gas wouldn't be very good. Okay, so that's the point. So we can the radium can decay into radon by this decay, the 4.871 or the 4.685, that leaves you with an excited nuclei that can later decay by emitting a photon to the ground state. I'm going to get to this type of process soon, because this process here is described as it says here, the gamma process. Okay, where you actually emit photons by transition between two energy levels in an excited nuclei. Okay, so this is one way to actually walk through this line. See, this over here is the stability region. And if I have a nuclei over here and I want to reduce the number of nucleons inside the nuclei, I have to walk down. If I go down in diagonal in a 45-degree thing here, it's a several of alpha particles, because you reduce the number of neutrons in 2 and reduce the number of protons in 2, and so essentially you go down in a 45-degree angle in this graph, and that will be an alpha decay. Okay, a beta decay is a decay that brings a nuclei along this line, depending on the sign of the beta decay. Plus beta decay or minus beta decay is going in this direction or that direction. We'll see that in a moment. The gamma is not reflected here because the gamma leaves everything intact. It's the same nuclei with the same number of protons, with the same number of neutrons. The only thing that it changes is the level of excitations of the nuclei. Okay, so an excited nuclei can decay to a lower or ground state by this means. Okay, so these are the type of processes that I'm trying to describe. This is the nuclear decay process, and the first one here it's called a beta decay. The beta decay produces electrons. This is an electron, so essentially you have a neutron. And from a neutron, you can go and transform the neutron into a proton emit an electron and also a very tiny neutral particle that have almost no mass. It's almost like a photon, but it has, you know, a very small mass, and this small mass particle and the electron that are produced carries the energy produced in this decay. Okay, the signs are very important here. This neutrino here is called an antineutrino of the electron. That's what is labeled with a line on top here, because they come in two flavors. You have the antineutrino and the neutrino here, and these are linked to electrons. There are three families of this guy. There are also some linked to other particles that are not linked to the electron, that they have a similar type of decay, which are the muon and the tau, which are not relevant for the topics of this course. Is just so that you know only, okay, that they are, you know, other neutrinos associated to other particles different than the electron. So these two guys are somehow associated to this decay. So we have we have the neutron that goes into a proton and emits an electron. Look, the sum of these two things, the charge of these two things is 0, which corresponds exactly what it should happen, because the neutron is a neutral particle. It has a charge distribution inside, so that's why things are reoriented somehow in order to create this particle over here. And essentially, people that measure this type of decay, actually they discover, let's say you have a neutron in you know, and standing still in a reference frame. So if that neutron will decay, it should emit, it decay in two particles. It should emit a proton in one direction and the beta in the opposite direction in order to conserve linear momentum in the system, because the neutron originally had no momentum. Okay, so but that didn't happen. People actually found out that there was an energy distribution for the electrons coming out. Okay, so this is the way they actually discover the existence of the antineutrino. Okay, a similar decay occurs also with the proton. This process here can occur in vacuum. This can only occur inside a nuclei. Okay, why? Because the neutron is actually heavier than the proton. Okay, and this is also a process that occurs and this is a sort of beta type process in which a proton inside a nuclei captures an electron and transforms itself to a neutron emitting a neutrino. Okay, so this type of processes don't change the A number. This type of process only changes the charge, the balance between N and Z inside the nuclei. Why is that? Because you can see that the number of nucleons in this side is the same as the number of nucleons in this side. The only thing that is different is the charge that they may have. Okay. Gamma decay. I was talking before about gamma decay, and you have an example here of a system that, if you remember well, we can actually model the nuclear interaction. This is energy in this axis, and this is position. So it's a potential well, essentially. And so this is a potential well with energy levels, as we know. Any potential well has energy level. And if we believe that the protons and the neutrons should have, you know, almost no difference inside the nuclei, because the nuclear interaction is much stronger than the electromagnetic interaction. If you have these levels around here, the proton and the neutrons should feel the same, you know, interaction. And essentially, for this level, I could put in this level of energy here for any nucleons. I could put two protons in blue here, and two neutrons in magenta, for example. Okay, so essentially, how would this happen? How can I change? How can I see a decay in emitting a gamma ray or electromagnetic radiation? Is simply that a particle in an excited state, like a proton here, similar as the electron would do in an atom, we make a transition to a low energy state, and the difference between this level and this level, the difference in energy, is emitted as a gamma ray. So essentially, this is an excited state, and then you have a lower energy state with the same nuclei, with the difference that this particular proton will be occupying a lying energy state around here. Okay. Okay. So this is a particular chain of decays in this Segre chart that I was talking to you about before. So here we have, for example, uranium-238, which is actually radioactive. So if we look at the chart before, uranium-238 was not in the chart because obviously this is only stable nuclei, okay? But uranium-238 exists, and it has a relatively long lifetime, actually. How long is the lifetime of uranium? Here it is, 4.47 times 10 to the 9 years, okay? Well, 10 to the 9 years for me is almost stable, you know, but not as a definition of a stable nuclei. Okay, so this guy is way above the stability region. So what does he want to do? Well, you know, this is the I'm sorry. So the idea is that from up here, this nuclei want to get to the stability region. This is where we want to be, because this is an excited state of matter, and you don't want to be there for a long time. That's what, you know, nature always does, find the lowest energy state possible with the similar conditions, okay, for the nuclei. So this guy starts going down. These lines over here along this 45 degree with slope 1, and going in steps of 2 and 2, this is an alpha particle decay, and you can see an alpha particle decay there. So there's a chain of alpha decays between all these things, and when you do that, you're actually changing the N, the C, and also the A, because you're going to a different line like this, different blue line. Remember, each of the blue lines here is constant value of A. So these transitions over here are beta. So when going from let's say from thorium-234 to uranium-234, and you can see it's 234 and 234, constant A. So this has to do with beta decay. Okay, so well, it's actually shown here in this part of the diagram. So this is the alpha, and that's a beta decay. So going in this direction is beta minus. Why does it mean beta minus? It means that you are actually increasing the number of protons, because if you have a neutron and the neutrons emit a negative charge, you need a positive charge in the parent nuclei, which is the proton, and that's why a decay in this direction means a beta minus. A decay in the other direction means a beta plus. This chain over here of decay, it's not casual, meaning there are a few of these. There are 4 or 5 that has been described. So sometimes an element arrives here from some region, and then it starts going down this road. Okay, but definitely they have to do with the decay of this relatively unstable nuclei, which is uranium-238. Okay, this actually, the uranium-238 is you know, it's the it's the more abundant isotope of uranium. The other one that they are fighting the Iranians for it's uranium-235. They are enriching uranium, meaning what does enrichment means? Enrichment means putting more uranium-235 in a piece of material that has uranium. Okay, 238 is the natural way you find uranium, and in the more abundant way, there are only a few atoms that are 235, and to do that, to separate this, you have to actually hand-pick them, meaning you have to separate, take out all the 238s and keep the 235 if that's what you want. And to separate that, they use them, the effect that the 238 and the 235 have different masses. And if they have different masses, the 238 of them, you may have actually heard about this, they put them in centrifuges. The centrifuges, you know, the effect of the centrifuge in something that has a mass that 238 is different from something that has a mass 235. And exactly that's what they use to separate the actual isotopes of uranium-235. I don't know all the details of the centrifuges because otherwise I could be dead. But you know, it's not something I want to do. Okay. But you know, the technology is there to actually use the centrifugal force to actually separate the both nuclei. Okay. Yeah. The other question that I wanted to address is why do let me move this way too. Why do beta type reactions occur inside a nucleus? Okay, so here again I have my potential well describing the nuclei. So and I have these energy levels inside, and in this particular case, I have an odd number of protons inside the nuclei and an odd number of neutrons, but I have one neutron less than the protons. So this guy, you know, all the particles are very lazy in nature. So this guy wants to be in a low energy state. Okay, so how do I get to a low energy? I cannot get to a low energy state by being here. Why not? Well, you cannot do that because this is a fermion, and each of the fermions are allowed only 2 per energy level inside. Okay, so these are the 2 that are there. These guys are also fermions, but are different particles. So they only allow 2 of the same kind in each energy level. So I have here the 2 protons, and I here have the 2 neutrons. But you know, this guy is looking at this unoccupied level here and says this is something advantageous. I have to decay from here to here, and I will have a nuclei which is more stable with less energy. So how does it do that? Well, you know, this is the original nuclei that has Z, which is the number of protons, is equal a half plus 1. So it's half of them plus 1 are protons, and half of them minus 1 are neutrons. Okay, so making a transition from here to here is only possible if this guy becomes to be a neutron. Okay, and how does it do that? Well, we have this mechanism, this reaction. This proton can go into a neutron, emitting a beta plus particle. The beta plus particle is a positron. A positron is the same particle, is the antiparticle of the electron. Essentially, it has the same mass but opposite charge. Okay, so we are not familiar. We live in a world where the prevalent particles are the electrons and the neutrons as we know them. But there could be you know, a parallel world where the matter is made out of antiprotons and positrons. Okay, and they would be as stable as the electron. Okay, Actually, the positron doesn't decay. The only way it decays is by recombining with an electron. And the positrons actually don't live very long because the world in which we live is full of electrons. So whenever there's a positron around, I'm sure he's going to find an electron boom and disappear and transform its energy in a gamma ray. Okay, so this is the equation that holds. And why does it happen? Because this guy wants to lower its energy to this place to get to be a more stable configuration. For this to happen, it means that the total mass of the initial ion, of the initial, nuclei, should be greater than the energy of the final nuclei, plus the energy to produce the beta plus particle, which has the same mass as the electron. That's what it's me times c squared here. So c squared times the mass of the original nuclei should be greater than c squared times the mass of the daughter nuclei plus the mass of the beta particle. This should be, strictly speaking, larger than this amount here, because the difference in energy should be provided as kinetic energy for these guys, for all the particles involved. Even these nuclei, if this is actually standing still, let's say it's standing still in a reference frame, these three particles should move away from each other in such a way that they should conserve energy and momentum. Okay, so the total momentum on this thing is also something that we have to verify that it's actually conserved in any of these reactions or transitions. Okay. The free neutron is unstable. Why do we know this? Because the neutron has an energy which is a bit higher than the proton. So if I didn't find the number, but the lifetime of a neutron, of a free neutron, is approximately 10 to 15 minutes. So that's how long a neutron will live if it's not interacting with other particles. Okay, so a free neutron lives about that. And what drives this transition is that there is a difference in mass. This is the mass of the neutron, as you know, the previous lecture I showed you is something a bit higher than the mass of the proton. So the neutron decays into a proton plus an electron. So it must have enough energy, the neutron, to actually transform itself to the proton and the electron that comes out. Okay. And you know, if we do the math here, it comes out positive, and the difference in the energy, it would be the amount of energy that is split among the constituents of the final products of the reaction. Okay. How they share? They are sharing in a way that they should conserve linear momentum. Okay, that's what it is. So the excellent in energy goes to kinetic energies of the beta, the nu E, and also the proton. Okay, if this guy can move, you know, it can hold some part of the energy. It usually takes very little energy because it has a very big mass compared to the mass of the electron and the antineutrino in this reaction. So essentially all the kinetic energy is really here. It provides a little bit of momentum, enough momentum to actually compensate the momentum taken away from this guy, that since the mass is too big, the kinetic energy is very small. Okay. You cannot do this in vacuum, though. You cannot transform the other way around. A free proton cannot decay into a neutron and a positron plus a neutrino. We also know this out of experience. The most abundant material in the universe is hydrogen. Okay, hydrogens are essentially free protons surrounded by an electron, which it makes no contribution to the stability as a nuclei. So there will be no hydrogen if this guy would decay. The lifetime of the proton has been predicted to be of the order of 10 to the 35 years. Okay? They have been measuring the lifetime of the proton in sort of sophisticated experiment where they actually try to find this type of process. They are trying to find the neutrino and the beta to see if actually this can go on and happen. And as far as we know, it's the lifetime of the proton is infinite. So just be sort of happy that it is like that, because otherwise water would disappear. So this type of reaction can occur inside a nuclei, because the mass of the neutron is this cannot. They can only proceed inside a nucleus, only because the mass of the neutron is larger than the mass of the proton. So if this has a mass that is larger than this one, this cannot produce in vacuum. But I show you here in this part of the view graph that a proton can go into a neutron if it when it's inside a nucleus, because there's an energy gain here. This delta E is an energy gain because of the energy levels inside the well. So a confined proton can decay, a free proton cannot. Okay, so that's the message behind. So we have this summary of decays here. The alpha particle, the beta particle, and now we want to examine a bit more of nuclear reactions, and let me see. And for that, what I have been doing so far is actually looking at how nuclei spontaneously decay into something different. But I could actually induce nuclear reactions if I put two nuclear entities together and generate something that's unstable, and they mix together and they produce different products. So this is sort of the model, the one that I'm showing here. You have particle A and particle B. These are nuclear matter, and you mix them together and produce particle C and particle D. Particles A and B are forced to interact. Okay. I assume there's no potential barrier in between, but if there is, I have to supply that as kinetic energy in such a way that the potential barrier is overcome. For example, if this nucleus is charged and this one is charged, if this could be a nuclei and this could be a neutron. If that is the case, I can just put this guy very close to each other with no cost in energy. But if this guy is a nuclei and this is an alpha particle, I have this repulsion that I have to overcome. So I have to give the alpha particle enough energy to get inside the nuclei for this reaction to happen. Okay. But even if that's the case, this quantity here, it's a very important quantity. It's the Q value of this reaction, which says you just sum the masses of the initial guys, the A and the B's, and subtract that from the masses of the C's and the D's, and multiply that by C squared. And this Q value is going to be the amount of energy that you can actually split as kinetic energy in the products. If Q is greater than 0, this is an exothermic reaction, and the mass of the system is certainly reduced. The mass of the product is certainly reduced, and the difference in energy, this Q value, goes into kinetic energy. If Q is less than 0 for this reaction, it means that it's an endothermic reaction, and it means that you'd have to put more energy in for this to occur. Okay, that is the key point here. And as it says here, care must be taken into account for the electrons of the nuclei not participating in the reactions. So when I have mass of A here, usually I put a neutral nuclei, and here also, and here also. why, even though it could be the bare electrons sometimes that are reacting, you know, if everything is compensated in terms of the electron, I'm sorry, the bare nuclei which are reacting, this relation, usually it's written down with the neutral particles. It doesn't make that much of a difference for two reasons, because the electrons, if you have the same numbers of electrons in this side and on this side, the equation will always be equilibrated. Okay, that's what it's something you have to. As I mentioned to you before, if charged particles are involved in the reaction, the alpha particle or the p particle, this is charged an alpha particle or a proton, you really have to overcome the repulsion barrier. This repulsion barrier here has to do with the charge interaction, the electromagnetic interaction between particles, and you really need to get to this particular radius, which is the nuclear radius, for the interaction to be actually overcome by the nuclear interaction, and you get the alpha particles sucked into a nuclei, for example, like that. So this is the idea. Okay. One of the most important, there are two reactions that are very important and polemic actually in this time of finding new ways of producing energy. One of them is the fission reaction that I'm describing here. Fission means actually splitting the nuclei. Okay, and this is this is an activated process, and this is why getting uranium-235 is so important. I'm actually showing here the prototypical reaction is uranium-235, I'm sorry, that is actually bombarded by a very low energy neutron or high energy neutron. It doesn't have to be very high energy. The fact is that the neutron can get inside the nuclei only if they collide, and you don't need a very high energy because there's no electromagnetic repulsion between these two particles. They essentially the uranium nucleus and the neutron don't see each other until they are at the distance of nuclear radius where the interactions are strong. Okay, and when that happens, you get an excited uranium-236 that actually decays into this barium, this krypton, and 3 additional neutrons. When you actually do the math here, calculate the Q value for this reaction. So you have this guy, you put in the neutron, and you know, sum everything here, and it always come out positive. And how positive? About 200 mega electron volt positive for each nuclear reaction, for each one of these things. If each one of these reactions were done with chemistry, meaning I'm trying to oxidize hydrocarbon or something like that, you can do an equation sort of like this, but not involving the nuclei, involving the electrons and how the atoms recombine. The energy that will come out for each one of those reactions is in the electron volt range. So this is 210 to the 6 times more energy for each one of those reactions. So this is why nuclear energy is so relevant. Okay, energy means heat. Energy means that an important fraction of this thing given as kinetic energy to the products you can use to actually warm something up. And if you warm something up, you can do a cycle like a turbine and whatever and take energy out. Okay, or if you don't control the reaction, you can actually make a bomb because it's much more stronger than dynamite or any you know, legal explosive that you could actually find. Okay. So the reason with this, the reason why this is always true, that you can get a lot of energy out of a fission reaction, is exactly this sort of shape. Look, this particle here is less, this is a heavy nuclei. A heavy nuclei sits around here. So if I split this guy in two smaller nuclei, each one of those other nuclei will sit over here. So this, remember, this is the binding energy. This is wrong here. This is the binding energy per nucleon, EB divided by A. So the binding energy per nucleon of the products of the reaction will be around here, and the binding energy per nucleon for these are the daughter nuclei, and this is the father nuclei. For the father nuclei, it's lower. So it means that these guys are actually tighter together. If they are tighter together, it means that they have to release energy to get to this point. How do they release them? Here it is, 200 mega electron volt per each one of those divisions. Okay, this is the way the fission product looks in the case of this is the frequency of products that you get out of uranium-236. Okay, so this is one of the math. Essentially, they split in half, not exactly on half, because half would be around here. See, but you know, there's this fraction and there's this fraction. So when you put you have to get to a mass of 236. So you go to something about 100 and something about 140. Okay, so when you produce this product, that product comes accompanied by this product. That's why this frequency or this yield here has almost the same value. So this is a let me explain again what this graph is, because I went too fast here. This is the number of fragments that you measure out of the reactions, and this is the Z value, the A value of the fragments. Okay, so the A value of the fragments should add up to 236. Okay, this is what it should do, because that's the original nuclei that is actually splitting. You put a neutron in, the neutron goes into uranium, it makes uranium-236 in an excited state, and this guy decays, and these are the fragments that you get. Okay, and so the addition, if you have this guy, probably you will have to get this guy in order for this and this to sum to 236. So essentially, there are two fragments every time, and not only that, there are two fragments, and they are also neutrons. So as a product of this thing, there are many neutrons. The neutrons are in excess. Why are the neutrons in excess? Because if you remember this graph here, you know, these guys, the heavy guys, have a lot of neutrons to be stable. Everybody wants to get stability here, you know, just like human beings, nuclear are the same. So these guys have a lot of nuclei to be stable, but this guy here needs less nuclei to be stable. When you split a heavy nuclei, you need less neutrons to be stable. So just get rid of them. You know, that's what nature tells you, and that's what they do when they have to go to these reactions. And this is the reason why you get extra neutrons for each reaction. And look what happens. You need a neutron to actually start the reaction of uranium-235. But out of the excitement of producing the uranium, and you get a fission, and you produce products, but then you produce 3 additional, essentially per reaction, you produce 3 additional neutrons. But with each one of these neutrons, you can actually fire up another uranium-235 to uranium-236, and the chain goes on. And you can see the multiplying effect here. You know, this guy produced 2, this 2 produce 4, and this is what is called a chain reaction. This is something you don't want to be close to when it happens, because you know this. If you want to get the good part of the energy out of uranium, you really have to control that this doesn't happen, because this is a bomb. Usually the geometry and the way you dispose the fuel cells, the nuclear fuel, it's something that's very important to actually achieve you know, the peaceful use of this. Okay, so this is the great thing about fission. The bad thing about this thing is that the lifetime of the products that are around here goes to millions of years. So essentially, you can use this thing to produce energy. The energy that produced doesn't give you CO2 to the atmosphere, so in the sense it's greener. Well, you know how green. You produce nuclear products that are going to be sitting around without the possibility of generating any energy, and you have to keep them for 10 to you know, the 6 years before this actually thing. It's, you know, it's something that you could sit on after a while without dying. So if we do this very often, we will find places radioactively hot that are not going to be able to you know, this matter has a lot of neutrons still, and they have to get rid of the neutrons somehow. Okay, and this is a process that takes a while and takes time. And so this is why nuclear energy is not really a solution. It is a spectacular in terms of the efficiency of the amount of energy you can get per material. You know, you can, you know, probably you can build a bomb.
I think it's like, if I'm not wrong, I think 1 kilogram of uranium 236 actually can release the same amount of energy. I think it was over like 100,000 or perhaps like 1 million kilograms of coal.
Yes. So the numbers are staggering. It has to do exactly with the same thing that I told you before. The coal gives energy in the electron volt range, whatever you do with it. Okay. The uranium is 200 times 10 to the 6. Okay, so it's 10 to the 8th. So whatever amount of carbon you have to divide that amount of carbon by 10 to the 8th kilogram unit, whatever atoms, whatever you want to call it, and then you are in the range of the amount of uranium that you will need to produce the same amount of energy. Okay, so it's really an impact, you know. It's and it's great that it is like that. But you know, I couldn't go out of this course without telling you this is the solution, guys. Here you have it. Okay, you're looking at it. This is a fission reaction. Fission means this is what we want to do is separate nuclei. I'm sorry. What I'm doing here? No, this is wrong. This is not. This is misspelled. This is fusion reaction. This is not an I. This is an U. Okay.
Yeah, actually, I have a small question about the notations. Fusion reaction. We have hydrogen and hydrogen, which makes a hydrogen 2 and a beta particle. But what would be the other particle? I don't particularly recognize that one.
This one?
Yeah, that one.
This is the neutrino. Okay.
Okay.
So this is the same guy that is in the beta decay here. This guy. It doesn't look like it's this guy actually. Okay. It's the proton going to a neutron, going to a beta plus and a neutrino. Okay. So let me get into the notation because I haven't actually explained this, because this, like in chemistry, you really have to count all the nuclei in both sides of the nucleons in both sides of the equation. The number of here is the A and the number at the bottom is the Z. So usually people drop the C because the C is equal to the symbol. So H, we know is 1. So whenever we have H, we have 1. Okay. But the top part here is the number of nucleons in the particle. This is a proton and this is a proton, and this guy over here is deuterium. Deuterium is a hydrogen atom that has in addition a neutron. Okay, so it's a bound state of a neutron and a proton. Okay, and this reaction, in order to have this, you have to transform one of these guys into a neutron in order to have the same number of nucleons in this side and in this side of the equation. How you do that? You generate a beta plus. So this guy carries the charge, the positive charge away, leaving a neutral particle in the nuclei. But this reaction is exactly, this is a beta plus reaction, what is going on here. Okay. Now you take this guy and make it react from this reaction, make it react with another proton, and you produce tritium, which is no, this is not tritium. This is I'm sorry, this is helium-3. It doesn't have a word. I don't have a word for it. It's helium-3. It is helium because there's a 2 down here, so the Z value is 2. It has 3 particles, so it has an additional neutron inside, and this particle, what do you do with this guy? The only thing is, when this guy gets in touch with this guy, it must release a gamma, okay? Because there's no change in the charge number here, because the charge number it's correct, meaning in this you have the Z value that you have is 2, and the Z value that you have here is 2. That's perfectly correct. Then you get this guy and make it react with another guy of this, and you make helium-4 plus 2 protons. This set of reactions that I'm showing you here, essentially you need to start from 4 protons to actually produce this, because you need this guy, if you do the math around, you need 4 protons to start this chain, okay? And what do you get at the end? You get at the end of this reaction, by joining the hydrogens in the proton chain, you form helium, and you get an energy Q about 24.7 megaelectron volts for this reaction. This reaction is exactly what happens in the sun. Okay. So why does it happen in the sun and we cannot make it here? Well, you know, there's a little problem here, because to get this guy in close contact to this guy, you have to overcome the Coulomb repulsion barrier. Okay. To do that, you need to, just send these guys colliding in front of each other with very high energy. Well, you can do that in an accelerator or whatnot, or you can, build a gas, a plasma with protons inside, and you just give them, a very high temperature. So there's going to be a high likelihood that 2 of these guys will collide front to front and join to form deuterium. Okay. So that is the main problem of generating fusion, not fission, fusion, on Earth. You need to generate a stable plasma with this mechanism. And look, there's, the only thing that could get out of here is hydrogen, which we have. These are the products that we have. Helium. We can use it in NMR or whatever. We will have a lot of helium being produced on Earth if we do this thing. There's nothing bad about this, guys, of the products of this reaction. So the fusion reaction is really what we should be doing. And the problem that we are not doing it right now is because technologically, it has not been possible to solve the problem of stabilizing the plasma you need to actually produce these reactions with enough stability. Okay. And at the current time, what we're doing is actually we're leaving out of this reaction. This is the reaction that gives our energy today. And we should be better take care of it, meaning if that's the sun, we cannot do anything bad about it. This is the reaction that gives the temperature to the sun, that gives you the radiation in the visible light at the end. And you can actually take that light and use a semiconductor device like a photocell to get that energy to charge your batteries, and forget about the fossil fuels. Okay, that's what we need to do. So nuclear reactions are the future in a sense. It will be very nice if fusion is used. There's people that argue that nuclear energy, as with uranium-235 going to uranium-236 when excited by by a neutron. Actually, there is no bottle of uranium-236 that would explode. The only thing that happens is you have uranium-235, which is, if you have it free from neutrons, it's perfect. It's a stable material. As soon as you put a neutron in there, you can generate a chain reaction. Okay, but this guy is great. It gives you, it doesn't give you 200 mega electron volt by reaction, but who cares? You know, there's no single product which is better than this reaction. So this is going on the sun, and it would be just great to do it here. Okay, so this is the way it looks. So you have the two protons, you make the deuterium, you generate these particles, then you have another proton, which in the sun they are plenty because this is almost all is hydrogen, collide with this particle here to generate a helium-3. And this helium-3, how does it say here? Well, it's actually decaying, and if I get this guy together with this guy, the helium-3 with another helium-3, it means that I should, to generate this guy, I need another 2 protons, okay, and I need this additional proton. But this reaction gives me 2 proton bags. So essentially, if I look at the whole cycle, this is a cycle where you end up beginning with 4 protons, and the final product is 1 helium atom. These guys you are just giving back because you need it here and you need it over there. Okay, so when you do the whole balance of this reaction in this way, as I'm describing, you get to this. You get to 24.7 mega electron volt per reaction. There are other reactions that are being technologically pursued to actually the less efficient, like the 24.7 reaction of helium. Why helium is so great is the reason is here. It's because this is a very strong peak. There are things, there could be things around here. You know, they are also in the mega electron volts. You can get this guy colliding with that guy and produce something here, let's say. Okay, so or even higher here. But those guys over there, they you know, it's not as great as with helium. So it's not going to be as efficient. I don't have it with me, but they are in the text, the other reactions that people are considering. Okay, so this is it. This is the end of it. You know, and I don't, there's a lot of physics that one has to learn to actually understand technology for the century that you guys are going to be living. So I hope this is a help on getting a good professional life for you guys and actually making a contribution to science and technology somewhere. Okay. If anything, I hope you have enjoyed this, looking at this. 2 things. Next Tuesday we have the finals, I assume.
But I sent you a mail asking if that could be moved to Thursday.
You sent me an email that you want to move it to Thursday.
Yeah, and actually you did respond that you had absolutely no problems in actually moving the finals to Thursday.
If I said that, it means that perfect. Let's move it to Thursday then. And no problem. 2 things. There's going to be a question in nuclear. Definitely, it's going to be a question in nuclear in the final. There's going to be a question on semiconductors. Definitely, it's going to be a question on semiconductors. Okay, so don't avoid looking at the last lectures before doing the rest. Okay, so looking at the details of the rest. Okay. So that you know, guys, you know, don't find surprises. Usually when somebody studies these topics, they start from the beginning and never look at what's on the end because you don't have enough time to work on it. Work on the final things first and then look backwards. Okay, that's my advice today. Okay,
Sandal.
So there's no lecture next Tuesday. Okay. Unless I'm going to be here, so unless anybody has questions or you want to do something, we could, you know, let me know by email if you want to sort of discuss a problem, something you don't understand or it's unclear, I'll have the time I can dedicate, not only on the regular time that we have the lecture plan, but any other time. Okay, so feel free to actually do that. Okay.
Yeah, that would actually be really helpful.
Yeah, so we can do this through email. If you guys decide on something, drop me a note. The only thing is that you have to remember that Tuesdays and Wednesday I also teach another course before you guys. So you're not gonna want to do that at 8 o'clock, so no problem. Okay, so this is it, the end of it. Okay, so but just be in touch in the sense that if you find something you want to talk about something, I'm gonna be here next Tuesday anyway. I'm not gonna prepare anything. If you want to talk, log in. Okay, we can chat about this and agree on a different date to actually meet if you want. Okay.
Right. Thank you very much for that, and
Okay.
thank you very much for this semester's course.
Yeah, it's been an experience for me too. So I hope you guys have enjoyed. There are many defects on this thing that could be overcome with practice and improving methodology. But this is such a fun subject that it's next time it's going to be better. I hope you guys are not there. No, you're not going to be there, definitely not. So you can come as a visiting student to actually verify if I'm doing the job correctly. But that's about it. Okay, guys, this is it. See you next Tuesday if you're there. If not, no obligation whatsoever. Okay.
Right, perfect.
Ciao, ciao.
See you next Tuesday. Goodbye.
Ciao.